Alright, so my headset is going to die. I need a moment now, so let's try to get this over with quick, partially because I'm also tired. So for this question, part one is a little bit somewhat straightforward. It's pretty confusing conceptually, but once you get it and you steal some code, then it's not too bad. So let's go ahead and parse all these into our hailstones. So I'm going to create a class, just to make it simple. So class hailstone. And then inside of here, we're just going to figure init, self line, and I'm just going to read in all of our variables, x, y, z. Our dx, dy, dz is equal to, and let me import re. I have to int on re dot find all, I believe. Yes. And then optionally a negative sign, and then read any number of digits. And we'll read this on our line. And we'll do self.positions is going to be equal to, we'll just put into a list, and self.velocities is equal to vx, vy, vz. Alright, so now we have this, and we'll create our hailstones is equal to hailstone L for L in input.split lines. Then I'll print out hailstones. Alright, let's see what exception we're getting. Oh, I have these as D's. Okay. Alright, cool. So now we have all of our hailstones getting read. I'm just going to assume that it works. And then so now for part one, we need a way to figure out if lines intersect. And so, bang. If you Google it, this pops up. And so if you have these 2 points, you can basically fit this into this function and it will give you yes or no if it is in here. So let's go ahead and modify this for our purposes. So here, now if we take all of this, we'll indent this once. And if we look, this basically takes in 2 kind of sets of points in like a 2x2 tuple, like kind of in this format. So let's change this around a little bit. So we'll take one as self and one as other. And then we'll do line 1 is, or we'll do here, x, y, and then something is equal to self.p. And then vx, vy is equal to self.v. And then what we'll do is line 1 is equal to our xy, and to get another point, we'll just do x plus vx, y plus vy. So now that we have this, what we'll do is from this point on, we'll do the same thing for the other point. So if we go ahead and do this now, and then we'll just change this to other, and we'll do the same thing here, and change this to a 2, and now we should be having basically working intersection code, except one thing is I don't want this to raise an exception. Let's just go ahead and return none, none. And then also we want to make sure that we are returning points that are in the same, like forwards in time. So if you look at like this, for example, here, they cross in the past, so that doesn't count. So let's create a function to basically take in these points and see what time they intersected at. So we'll do def get time self and x. We'll here we'll do is in future. So what this will do is basically take in some point and x value and tell me if this point was in the future or not. So to do this, we basically can just write out the formula where it's if I have my self.x plus self dot, or I'll just say this, x plus dvx times t is equal to our new x. This is basically just the regular formula that we currently have. So now, if we want to solve for our t and see if it's positive or greater than or equal to 0, then we can just subtract. So we'll have nx minus x, and then if we divide all of this by our vx, then we get our t. So this is just like algebra. And then what I'll do here is, if this greater than or equal to 0, I'll return this. And then now we just need to define our variables. So x will be self.px, vx will be self.v. And I believe that should be good. I'm just going to run it to make sure nothing compile errors. Cool. All right. And then now inside of this code, let's go ahead and do if. So if is self.is in future on our x value and other dot is in future on this x value, then we'll return this. Otherwise, we'll return none, none again. So now we should have this valid working intersection code and a way to check the time. So now for part one, what we'll do is we'll do, what's a nice way of doing this? First we'll have p1 is equal to 0, and we'll return this. For I in range len hailstones, -1, and then for j in range, I plus 1 len hailstones. So basically this is iterating through, like, for example, if I was iterating through this for some reason, I is iterating through each one of these, and then j is iterating. So for example, if I is here, j is iterating here. If I is here, j would iterate here, so forth. So now this is how we get every combination. We'll do xy is equal to hailstones at our I dot line intersection with hailstones at j. So now if x is none, we'll continue. This is one of our cases here or here. And this case is if they don't intersect, by the way. So now we'll do this, and then if we'll make sure, so I'll write this kind of, we'll also kind of write our test area. So we'll do test area, I'll say TA is equal to 7 to 27 if len of our input dot split lines is less than 10. So if we have less than 10, we'll just say it's the debug case. Else, we will do whatever these numbers are. And there's definitely a cleaner way of writing this, but I kind of don't care because I'm tired and I'm sleepy. So I apologize. But here, now if I just run this, we should get no errors. Cool. All right. So now we'll go ahead and add in the if TA0 is less than equal to x less than equal to TA1 and TA0 less than equal to y less than equal to TA1, then it's inside the bounds, and we'll do P1 plus equals 1. And now let's go ahead and see. Cool, we get the right answer for the test case. If I run this, right answer here. All right, what time are we at? It's cool. All right, so now for part 2, basically they want to find one rock that'll hit every single hailstone. And so, first of all, that's very, very difficult to do. And so what pretty much everyone did is use some kind of external math library just to kind of crank out the math itself. You could probably write the linear algebra or whatever to solve this, but you don't have to if you just utilize the tools you're given. So we are going to use Sympy. Symbol and solve polysystem. So this is my first time using the library, but if I look at it, it's basically like a symbolic math solver, stuff like that. Other people use Z3, which I have touched before, which is another solver. But yeah, pretty much any kind of math library will work for this. But so, another observation people have kind of pointed out is you only need to test 3 hailstones to find the unique line. And I'm assuming it's, like, I probably need to think about it a little bit more, but it's something about the dimensionality. And like, for example, if we needed to hit this in 4 dimensions, we might need 4 hailstones, something like that. But it also could just be the minimum amount of points you need to fit a line. But either way, people have figured out, smarter than me, have figured out you'll need 3. So let's go ahead and start solving that. So the way to do this is I'm just going to extract this into a function to make it clean. Hailstones. And we'll call it from here. So P2 hailstones. So what we're going to do is, first of all, we're going to define all of these variables. Symbol C for C in XYZ, VX, VY, VZ dot split. So this is basically me just writing some convoluted code for no reason, but essentially I'm just saying x is equal to symbol of x. I'm doing this for each of these variables. I'm just kind of writing it in shorter notation just to make my code smaller. And now we'll go ahead and define our this VX, VY, VZ. This is just going to help us, and we're going to have a list of our variables because we'll need to throw this into the solver at the end. And we're also going to need a list of equations. So now for I and then hailstone, and enumerate hailstones, but we only want to see the first 3 hailstones because that's all we need to solve it. Then we'll do t is equal to symbol, and we're going to create basically 3 different time variables, because each individual hailstone can hit this new rock at a different time, so that's fine. And now for j in range 3, we'll do equations.append, and then basically the x, so for example, for one of these cases, what we're going to get is, so like if I say position at 0 plus velocity at 0 times t, this is the position of the first, or like our given hailstone at this time. If I subtract the hailstone's exact same thing plus hailstone.velocity at 0 times t, this will give me basically an equation satisfying the x constraint, saying, hey, at some time, at the same time for both of these, my rock and then this hailstone should be at the same position, and there should be some t that exists. And so we'll just do this for, instead of 0, we will do this for j, and then we can just do this for j in range 3. So now we've got all of these equations, and we'll add our t to our variables. And finally, if I print out sol polysystem equations and vars, you can see, first of all, it runs really quick, but second of all, it solves for our x, 24, our y, 13, and our z, which is 10, very quickly. And so now let's just get the answer out of this. So I'll get 0 because I want the first tuple, and then I want to get the first 3 elements and sum them together and return this. So now if I run this, you can see we get the right answer. And then if I get this and I submit this, we get the right answer here. Oh, that's not what I want to see. No, that's okay. Okay, that's weird, but yeah. So we are getting the difference is this gives us its own custom wrapped. It's like an integer or whatever. So we just turn it into an int. So yeah, with that we get the right answer. So yeah, happy solving.